Okay, so now that we have an idea of how to not only draw Lewis structures, but also use those Lewis structures in conjunction with VSEPR theory to come up with the shapes of molecules, now we're going to take a look at how we can incorporate both the shapes of molecules along with the polarity of bonds in order to now determine the molecular polarity. In other words, is the molecule polar or non-polar? And this is going to be important because the polarity of a molecule will determine some of its characteristics, both chemical and physical characteristics. So it's really important that we're able to determine this. Now, a couple things to keep in mind, first of all. A molecule, or when we look at determining molecular polarity, which is what we're looking at here, we first of all need to look at a couple things. We need to look at the polarity of the individual bonds that make up the molecule, and we've talked about bond polarity before, where we look at differences in electronegativities. So the polarity of the bonds in the molecule. And then we also need to consider the shape, the molecular shape, or the molecular geometry. Okay, so those are the two things that we need to consider. And just generally, we can say to make things simple, we look at the easiest example here. If your molecule is made up of, so if molecule is composed of only non-polar bonds, then the situation is very simple. That means the molecule as a whole is going to be non-polar. Okay, so that's the simplest example. If there are only non-polar bonds in the molecule has to be non-polar. The situation becomes a little bit more complicated now if the molecule contains polar bonds, so one or more polar bonds, then we need to consider the shape of the molecule. Now we need to consider the shape of the molecule to see whether or not if the polar bonds, which now remember the polar bonds, we can represent those using dipoles. So we can say the bond dipoles cancel out. Okay, and then we can answer that question. Well, the answer to that question gives us the answer to the original question that we're posing here. So we're going to consider if the molecule has one or more polar bonds, we consider the shape. If those bond dipoles do cancel, so if the bond dipoles cancel out in the molecule, then the molecule is nonpolar. And if the bond dipoles don't cancel, then the molecule has to be polar. And then we say, as a result of this, then the molecule has a net or overall dipole. Okay, that's the terminology that we're going to use. And we're looking at a couple things. We're looking at the polarity of the individual bonds in the molecule. We're also looking at the shape of the molecule. So for instance, if we look at a couple examples, and we'll look at simple examples to begin with. If we look at carbon dioxide, CO2, and you draw the Lewis structure for it, we see that carbon dioxide is going to be this structure, and you've drawn this before. And then if we look at the shape of CO2 using the Vesper theory, we know that the shape of this is going to be linear, right? So this is a straight line. It's 180 degrees between the bonds. So when we consider now the polarity of the individual bonds based on differences in electronegativity, we know that the carbon-oxygen bond, okay, this bond here, that is a polar bond, and the carbon-oxygen bond on the other side is also a polar bond. We know because oxygen is more electronegative that that bond dipole is going to be in that general direction, and then we have a bond dipole going in the other direction as well. Okay, so these are the bond dipoles that we have in CO2. Okay, the CO bond is a polar bond. And you can look at your differences in electronegativities to confirm that. So these bond dipoles then, so in this case, our molecule does have polar bonds. Do they cancel out? And these bond dipoles or these polar bonds do cancel because they are equal and they are opposite to each other. Okay, and you can think of as an analogy here, if you can consider that central atom, the carbon here being pulled in one direction to the left with a certain strength, and then it's being pulled in the other direction to the right with a certain strength. Overall, that carbon in the middle isn't going to feel a net pull in any direction, so there is no net dipole. So no net dipole. So as a result, the molecule then is non-polar. So carbon dioxide, even though it's made up of polar bonds, it's a non-polar molecule. And if we compare that with another very important molecule like water, H2O, okay, we draw the Lewis structure for H2O, and in conjunction with the shape, we see that it looks like this. Okay, and the shape here is a bent shape, according to Vesper theory. And we know now the oxygen-hydrogen bond, that is also a polar bond that goes in this general direction, right? You have these two OH bonds that are polar. Okay, and in this case, they don't cancel out. And the reason is because of, you can consider these dipoles as being vectors. You can split it into a vector, a component vector in the x-axis and the y-axis. So for instance, this orange one on the left here can be considered of a vector going this way and then one going that way, right? So it ends up as the same as the orange. And similarly, the one on the right, we have something going on there as well. Okay, so we have a vector going in one axis and one going in the other axis. So you can see these components of the vector in yellow, they will cancel because these are equal and opposite. But the component of the vector in the upwards direction in green, they actually don't cancel, they actually add together. So the overall polarity then is in this general direction from bottom to top, from where the H's are all the way up to where the O is in this molecule. So in this case, we do have polar bonds. They don't cancel. So as a result, H2O then, H2O is a polar molecule. And that's actually a very important characteristic for water, the fact that it's bent, but also the fact that it is polar. All right. So when it comes to these determining the polarity of molecules, you have to look at the polarity of the individual bonds, and you have to look at the shape of the molecule as well. We'll take a look at a couple more examples. So this is the case here of, I think we have carbon tetrachloride, CCl4. And that shape, as you probably know by now, this is a tetrahedral shape for CCl4, according to the Vesper model. Okay, so it's like a tripod with the head sticking out. So this is my carbon here in the center. Okay, I have chlorines all the way around. Each of the carbon-chlorine bonds are polar bonds. So all of those are going to have dipoles associated with them. Okay, and because these are all now equal and opposite, right, these will all cancel out. So polar bonds in the case of CCl4, so polar CCl bonds, they cancel. So as a result, the molecule then is non-polar. Okay, in the case of CHCl3, right? So again, here we have our carbon in the middle. Okay, and now we have our Cl's again. We have three of them, Cl, Cl, and Cl, but now we have an H up here at the top, right? And as you know from we talked about before, the carbon-hydrogen bond is not a polar bond. So we actually have three dipoles here, right? And these don't cancel out. And as a result, this molecule ends up being polar. Okay, so the same trend is going to, or the same idea you want to apply to even if you have more than four terminal atoms connected to the central one. So in the case of PCl5, phosphorus pentachloride, right, the PCl bonds, those are all polar bonds, but they cancel out because they're equal and opposite to each other. And because of the shape, the molecule then is going to be non-polar as a whole.